Sketching and matching derivative curves. If we are given the graph of a curve y equals f of x, we can sketch the graph of its derivative dy dx equals f prime x by using our knowledge of the sign of the derivative. Example 1. The diagram opposite shows a section of the curve y equals f of x. Draw a graph of the slope of this curve, i.e. construct a graph of dy dx equals f prime x. It is a good idea to line up the graph of the derivative under the given graph. So this is our given graph. This is our x-axis and our y-axis. So it's a good idea to draw another y-axis, a separate one, directly underneath. So here's our y-axis, and here's our x-axis where we will draw our derivative. Identify the key points on the given curve. A saddle point, B, a local minimum, C, a point of inflection. So we can see we have a saddle point here at A because we have a decreasing slope, a slope of 0, and then a decreasing slope again. So this is a saddle point. We can see we have a local minimum at point B because we have a decreasing slope, a slope of 0, and an increasing slope. So here we have a turning point, which is our local minimum. And at C we have a point of inflection. We have concave downwards and then concave upwards either side. The slope curve will be 0 at A and B. So at A, where we have a horizontal line, a horizontal slope, a slope of 0, we know that our slope curve will touch off the x-axis. And likewise at B, where we have a slope of 0, a horizontal line, we will also touch off the x-axis. At A and C, the slope curve will have turning points. So at A and C, the slope curve will have turning points. So we have a turning point, a maximum point here, a local max, and then a local min at C. To the left of B, the slope is negative. So to the left of B, we have a negative slope. It's going downwards, except at A. At A, we have a horizontal line, a slope of 0. And to the right of B, the slope is positive. So the slope is going upwards to the right of B. The same methods may be used to construct the graph of the second derivative from the graph of the first derivative. We may also be asked to match the graph of a function with the graphs of its first and second derivatives. Example 2. Below are shown 3 graphs A, B, and C. One of these represents the function y equals f of x, and the others represent the first derivative dy dx equals f prime x, and the second derivative d squared y dx squared equals f double prime x. So here we have graph A, graph B, and graph C. Part 1. Match the graphs of A, B, and C with the function y equals f of x, its first derivative, and its second derivative. And part 2, give reasons for your choices. So B is our graph y equals f of x. C is the first derivative, and A is the second derivative. Part 2, give reasons for your choices. So remember, this is the graph y equals f of x. This is the graph y equals prime x, so the first derivative. And this is the graph y equals double prime x, the second derivative. The graph in C has 2 stationary points. So here's our graph of C. Here's the first stationary point, the first turning point. It's a maximum. And the second stationary point, the second turning point, it's a minimum. Thus, its derivative will intersect the x-axis twice. So the derivative of this function will intersect the x-axis twice. As the graph of B intersects the x-axis 3 times, it cannot be the derivative of C. So it intersects here, here, and here. And it also has 3 turning points. The graph in A intersects the x-axis twice, here and here. Hence, graph A, must be the derivative of C. So graph A must be the derivative of graph C. This means that the graph in C must be the derivative of the graph in B. So C must be the derivative of B. So this is the graph y equals f of x. This is the first derivative. And this is the second derivative.